Start. Hello. The class before we looked at mobile IP, and for routing we saw two different ways of doing routing in mobile IP. One is the direct, and another one is indirect. Can you tell me, anybody remembers what's the difference between, what's the advantage of direct routing? Faster. And why is it faster? Right, so from correspondent to home network and from home network to visited network. And then the reply comes back. So that's what happens in the indirect. In the direct, you can, as a correspondent, can directly communicate with the visited network. That cuts down that indirection, and that's why it is better. In terms of privacy, which gives more privacy? Indirect gives privacy because the correspondent never learns which network you are visiting, right? And that's why it's more private. So this was all in terms of IP networks. And then before we stop this topic, we'll also look at in terms of cellular network what happens. Okay. So let me give you an architecture of cellular network. This is different from IP. So these are what we say a cell, and then what we see in center, instead of an access point, you see a base station, BTS. In technical it's called BTS. So this is a cell phone tower in our common terms. You have these cells, and then there are some cells which has one central higher level entity, which we say MSC. This is the switching center, and then there are different MSC within one area. If let's say this is part of Delhi, and then you will have multiple cells grouped together under one MSC, and then multiple MSC grouped together and connected to the backbone network, which is our wireline network. And these are all optical cables running across the city. Okay. Anybody knows why this structure? Is the cell actually an hexagon?
It's actually a circular area. This is the closest to the we represent.
Okay, so it's suppose in the ideal context, if you are in the free space, then it will be a circle. In reality, it's not even circle; it's a distorted circle, I would say. Okay, but then if it's a circle, why hexagon? If it's a circle, let's draw circles. Why do we draw hexagons? There is a skill, right? If you try to stack up circular discs in an area, you will see when you do that, there is some space that remains. There is no way you can fill up the entire area. And then this will never get a cellular coverage. This area will always be out of cellular coverage, right? So in reality, what happens is, instead of this, you have something like this. Lots of circles with overlaps. But then what happens if you do write anything in mathematics, right? We can't write this, always draw diagrams and write anything about it. Right? So to have simple equations and write mathematical equation on top of it, right? We approximate this to a hexagon so that we can cover the entire area. And then all our equations are in terms of this hexagon. Right? The sides of these hexagons are same. Right? And then you have all the property of geometry. Right? And you can write theorems and everything. You can write proofs about it. So that's what it is. Now coming back to the networks. Now this is our correspondent. And this is trying to make a call. And for now, let's see this is on the wired line. Right? How does this call land up finally? And then how do you get mobility? When the actual load moves, the destination moves from one to another area, what happens? So we'll start looking at this. Okay. So we'll draw parallels between what you've seen for mobile IP and direct indirect routing and this network. We will again say there is something called a home network. In cellular network also, we'll identify a home network and which will have a registry. So this is like an agent, home agent, which is maintaining a database. And so we call this a home location register. And this you have all the information about that particular user. A cell phone number, profile information, what kind of services, value-added services that person has got, and information about its current location. So whenever you switch it on, the towers in that area will look where you are and what is your ID and which network you are connected to and all that, and that will get stored in a database, in a registry, and that's always maintained. So this is one registry maintained in your home location, and then when you visit another network, you are in the visitor network, there is another registry which we say visitor location registry. So now if we switch it on in Bangalore, right, the same kind of communication will happen between the visiting agent and your home network agent, between them. And so in the visiting network also you will get an entry and it will tell, there will be a communication between these two networks and you get assigned a local number in that visited network. So if you are in Bangalore, you will get a Bangalore number. Right, and it's stored there. Now, can you tell me how is the routing would work out? We apply the same routing principle. Let's say you take indirect routing. Right, so our network is this. Now, right, this is your home network, and this is, let's say you visit. This is another network which you visit. How would the routing take place if you have indirect routing?
So, we first go to your home.
Yes, home register.
And then HLR will point to the location.
Yes. Yes.
Then it will just forward your call.
Right. Right. So this is indirect routing. Right. So you try to place a call from the correspondent. It will go to that backbone network. Then it will first go to the home network. And from the home network, you look up the registry inside your home network, and from there you find out where you are visiting, right? And the call gets routed like this, right? And that's why we have to pay more roaming charges, because when you do roaming charges, and you are actually paying for this call, not only this phone call, but actually you end up paying even if you are receiving. Right? So why is when you're roaming you pay higher receiving charges? Otherwise, typically you don't pay receiving charges. It's because you are paying for this call also. Right? And that call value is right, actually you have to pay. Even if you are receiving, you have to pay for this value. Same, right? So that is how why the call gets routed and it uses indirect routing. Right? So this is one architecture. I'm not saying this is what's being currently used also in the latest standard. But this was the standard drawing from the indirect routing protocol. And that's how finally the call will end up to the mobile user. Questions?
So registry maintaining a particular.
So registry is maintained. So this is your home network, this is your switching center, right? So that registry gets replicated also between, because there are different home MSCs. Right? And that's where mobile switching centers, and that's where it all gets replicated also. But that is always be maintaining at your home. Right? The entry gets added when you're visiting VLR only when you visit it. After communication between this and this. Right? The same authentication and profile checking and everything.
So in mobile IP, the advantage we have is that the IP could be traced to the geographic location. So for example, as the IP of the state network is so the IP, the home network gives you the IP when you trace it.
Yes.
For example, if I am visiting location register,
Right.
my number is being broadcast. So here, every single register will have to keep the database of the entire mobile. Because,
So in mobile also, right, there are, so first of all in the operators, right, operator you get the number divided, and within number also there are, I don't know the formula that they use, but from number you can find out which circle you belong to. Is it Delhi or some other circle?
more specific scenario is when you have mobile portability, the number portability.
Right. So that portability, it's not tied up to the number right now. Right. So that is a different thing. So in our country, we are using something which is a 10-digit one mobile number. But let's say if you go to US, right, you get a mobile number and a landline number, and there is no difference between them. Right? It's the standard STD prefix and then the number. Okay, so they use the same format, and that's how you get the number gets tied to a location. In our case also, the numbers are allocated region-wise, right? And the number portability is a different topic. Right? It's a different technology that they would use to allow you to do this. Right? But so far, the call gets routed like this.
So we are assuming that
Yes, there is a geographical distribution of numbers, telephone numbers. So that's between two different networks. One is the visitor network and this is another network. Okay? Now let's focus and zoom in and see what happens when you go from one cell to another cell or one MSC to another MSC. Right? Anybody knows what is it called? When you go from one cell to another cell. Hand off. So this is a critical process, and this is where typically you lose your phone connection. Right? Till today. And if you're moving, you're mobile, you're fast, like in a train or a car, something which is moving very fast, and you're talking to a person, and then once suddenly the call gets dropped, it's typically this is the culprit, the handoffs. Right? So it's because this has to happen in real time. So let me show you an example of what is really happening. So there is a mobile switching center, MSC. Right? Within that MSC, there is one cell phone tower here, and you are close to this one, and there is another cell phone tower. Right? And then your call is routed like this, right now. And as you move from one tower to another tower, and we are in this range, right? If you assume that now the signal bit from this tower is less as compared to this one, then you would like to get associated to the another tower. And that's where the handoff happens. But this is a little involved process. So the reasons of handoffs could be you are getting a stronger signal from the new tower. That could be one good reason. Another reason could be load balancing. One tower has got so many subscribers associated with it. Right? Let's say there is a stadium nearby and there are lots of people in that stadium. In that case, this tower is loaded. Right? So the other tower will take over. Right? In that case, also you can do a handoff. But as you see, the standard doesn't say when to do handoff. It's totally dependent on your mobile phone, your operator, and your base station. Right? When to do a real handoff. There is nothing mentioned. Standard will only mention how to do a handoff. When to do a handoff, it's open. Right? And it depends from operator to operator and so on. So can you think of a protocol where my call should not get dropped? Think of a protocol where a call should not get dropped, but you should list down all the steps. So this is one entity, this is second entity, and this is third entity, and this is fourth. There are four entities totally, right, involved in this process. So how would you hand off a call? If, let's say you are getting continuous data, what do you think should be done so that my call will come from here to here without dropping? Take a couple of minutes, think about it, but you should give me a right protocol. Right? There should not be any ambiguity about it. And certainly the call should not get dropped, and the call should not go to two different places also. That is also not correct. You can come up with a protocol where the call gets routed to everybody, all the base stations, all the towers. That's also not right. Messages, communication, whatever control thing you want to do, right? Think of all of that and tell me how would you route the call differently. Right, very good point. Do you need connectivity with both? So what she's asking is, when I am mobile like this, do I be in the range of both the towers at the same time or not? So you can make an assumption. If you write a protocol, you can make an assumption. So my protocol requires this. Or if your protocol does not require it, you say that my protocol doesn't require it. So that will be coming up with a protocol that does not assume you are within the range of both is hard. It's good to always assume you are in the range of everyone. If you get disconnected, whatever protocol you write, it's really hard to come up with that.
So when we are connected to the old PSS, and when we are doing the handoff, and both the base stations are actually of equal strength.
Right.
So for the equal strength, we can connect them to both the base stations for a short interval of time.
Right.
And then we do the handoff when the other single strength.
Right. So, but your now protocol assumes that you get connected to two towers at the same time.
Very short period of time when both the signals are.
Right. So we will debate whether this assumption is a good one or not. Getting connected to two towers at the same time. Typically, it's so you think about this. But so whatever assumptions you want to make, you can make it. I will just now then look at the assumptions you are making. Whether you can be in the range of both the towers at the same time. Second thing is whether you can get connected to both the towers at the same time. But you should tell, right, so the protocol will be this one sends a message or this one sends a message. Right? And what will be that message? Connection or disconnection? And routing of the call or not? And so on. Which basis? New one. Any basis?
Control messages or anything.
Right.
Information to the MSC also.
Yes. They have to. See, finally the call gets routed from here. That is the flipping switch. Right? MSC has to be involved in this process at one point where it changes it like this. Right? MSC is also
At no basis to actually. At no point should this be in rules. At no point at all should there be.
As much as possible.
Even for a small instance, there should not be.
As much as possible. But if you want that, you say, okay, for this much time it gets routed to both, I mean, that is your protocol. But as much as possible, no. Because then see, if you are doing this for the load balancing, right, you want to minimize the load on this one. So why to send the call there, right, for certain duration also? If you could just flip it like this, right, that would be the ideal scenario.
So the old basis could actually send details about how many users are connected and what is the signal strength of each mobile device that is connected to the main switching center. And the main switching center has to decide who the call has to be on. So, for example, let's assume that the user is just sending is a call connect and it is sending data to the basis. So, we assume that the basis is also sending the signal strength, and at some point of time, the new BSS gets the signal strength of the mobile number, and the MSC decides that okay, the new BSS is getting more coverage of that number.
Okay. So what you are saying is a centralized algorithm, right? Everybody reports to one central entity. He looks at everything, and he dynamic at that point decides it. Right. So computation, but it's also centralized. Right? Locally, you are not rerouting it. You send all the information to one central authority. He looks at all the entries and then decides and then tells everyone below that you should take this action. It's not a distributed program. That's okay when it's central. But plus, I want everybody else to take a couple of minutes. Right? Because you have to give them all the steps, not just one step. And so remember, this is an open question. No answer is correct, right? Or all the answers could be correct. Perfect. Right? It's an open question. Okay, in this scenario, we don't consider this one between two MSCs, right? So that makes it complicated. And this is where it stops. It's within the purview of scope of one MSC. So, right? If it's two MSC, even something goes bad. So in the bandwidth network also, we have to change routes. Right? So it's complicated. I will tell you about what happens between MSCs. But for now, within one MSC, how we should do it. Right.
So after that process, that check finds the second strength is depleted. So it sends the information back to the MSC and it belongs to the
Okay, you're saying some information goes from here to here, and it's telling about this. I think so. So what all of you have done is how this routing goes from here to here at the level of MSC and base station, right? Between base station and MSC. But the final thing, the call is here, right? Between the base station and the mobile node. What about them? Right. Right. Yes.
So you can actually ask the other stations to send out the controls.
Right. Right. But still, it's again coming back to base station and MSC. Don't you think you should do something between this node which is moving and the base station? Because finally, right, it's like this is child of this node now, and this is parent, and you're giving your child to somebody else. And you should first talk to the child.
strength is less than
Right. Well, so the routing is two parts. One is this one, and one is another one this one. Right? So you should be able to have this association also set up. So between this base station, old BSS, and the mobile, and that same BSS and the new BSS, mobile and new BSS. Right? So there should be a way of telling this new BSS also that you should take care of this mobile. Right? Are you ready to take possession of this entity? Right? And if you are ready, then do you have resources enough for this entity? Right? And then only in that case, right, you should hand it over to somebody else. Right? It's a property that you are handing from one thing to another. So first thing, this also should be in place. Then only, see, if this is not in place and you route the call here, right, the call will come here. But if this final last mile thing is not connected, then the call gets dropped. Right? So first of all, you have to make sure that all this thing is up, and this is very dynamic. And this is not dynamic. Right? There is actually a fiber line, optical cable running between the base station and this one. Right? So associating resources now this is easy. What is hard is this association. And you know that whenever a phone is associated with the tower, right, there is a lot of communication happening between them to stay connected. Okay. So, but what you said about this is almost correct. What happens between the old BSS and the new BSS through MSC. So let me give you the protocol. So old BSS, he was saying, informs MSC of impending handoff. Right? And the reason could be my signal that I'm receiving from the mobile, it's getting weaker and weaker. Right? So this tower knows that this mobile is actually going away from me. So the signal is getting lesser and lesser. Okay, in that case, this old BSS also knows which are the neighbors around it, which can take over. Right? So it gives a list of at least one new BSS or more, which are potential. Who can take it? Who can take this mobile node in their coverage? So MSC knows about it. Now MSC talks to the new BSS here. Right? And tells new BSS, so it does a selection. Out of this 1 plus node, right, it selects one and tells, okay, you should be ready to take possession of one mobile. Right? You should be able to do that. So allocate all your resources and be ready for that. So before it cuts the wire here, right, it actually first creates a new cable there, new connection there. So all that connection has to be there before you cut it off from that this end. Right, so the new BSS allocates radio channel for that mobile and it is ready for that. Now new BSS signal MSC that I am ready, and through MSC it also tells old BSS that I am ready now. Right, whenever you are ready, you can hand it over. Right, so now old BSS will tell the mobile. So far mobile is not aware of anything that is going to happen. And it is still in that same world of sending packets to the old BSS. So now it tells the mobile that you will have to be handed off. Right? Be ready for that. And this is your new base station. This is your new parent. And so you should establish connection to that. So mobile and the new BSS will signal each other to activate that channel which was allocated. Right? And at that point, this channel is also there, as you're saying, and this channel is also there. Right? So you are talking to this mobile, but the destination is single one through different channels. Still, the good thing about this is the data is not coming, or the messages are not coming out. This channel is there, right? But MSC has not yet flipped the switch from here to here. Right? So data flows like this, but the channel is there. There are two channels, active channels. So at a time, mobile is connected to two different tasks. At this point. So at this point. Mobile and UBS signal to activate each other. Now when this happens, mobile signals via new BSS to the MSC. Right? Because see, mobile is the only person or any only entity which can tell MSC finally that I have the other channel up and running. Right? This you count as this one. And because the connection has to be all the way from here to here. So it will use that new channel and the control path of that channel to tell MSC that I am ready to receive data on this new channel all the way. Right? At that point, MSC will flip the switch like this. The data will start flowing to this, and at that point, OBS releases all the resources. So you see, for you, it's just a very simple thing. You don't even notice a lot of times when this happens. You see, this is a little complicated process. It's communication happening between the base station and the MSC and the mobile phone, right? And so much of signaling is going on. So that's why handoff is hard. And sometimes handoff happens even when you are here. So if right now I am here, I am not moving much. Right? But one tower gets loaded, another tower is not loaded, I am handed off. Right? And all that thing. So a lot of times, even though you are stationary, your call gets disconnected because you get handed off between one entity to another entity. And sometimes the hands off are little misleading. This base station might think that your signal is getting bad, right, for a moment, and it does a handoff, right? But that bad signal was only for a moment. And then you again come back to that old base station. Because radio signals continuously change in the quality. That's a good point. So what happens is there are some channels which are shared. Right. Right. So there are some channels which are shared. So for data they are different. Certainly. For the control part they are same. They could be same. Right? Especially in CDMA they are the same. Right? So they are used. So nowadays on our phone we can't see it, but 2 years back you could actually see all the cell phone towers from which are around you, not just one where you are connected, but all of them. Right? So there is a shared channel which is announcing all this information. Right? So in that channel, if you are blocked, right, in that case you can hear from all. But of course for data you can't because that will interfere. Right. Yes. Right. So at this point, new bases will reject the connection. No. So new bases job is to just report to MSC. Right. If you can accept the connection, yes. If you cannot accept, it will say I cannot. Right. No, not call will drop. So MSC has got, if it has got a list of more bases, not just one, it will buy another one. Right? But in that region, if you don't have many other options, right, like the call might get this. After 8, this stops. These resources are released. Right? But now the call is acting like this. So during the handoff, call might get disconnected. During. No, not always. Right? Otherwise, why will you do handoff? Questions? So the steps are such that, right, there are momentarily connections from this and this, right? And there are 2 hops for the connection, this hop and this hop, right? First, you establish this hop and then also this hop. And then once this is established through mobile, you tell MSC that I don't anymore need this connection, right? So you just use this connection after that. Right? So mobile will tell the MSC. So step 7 is the mobile signal via new bases to MSC that this part is complete and I am ready to receive a call on this new channel. Right, so they activate the channel, right? But we should hear back from the final entity that it's fully done. So this is a process and this is when it finishes. Right? It is active, right? And you send back one message saying it is active. Right? It shows a green signal from mobile. And then the call gets routed in a different route.
Sir,
data does not be on two channels at the same time.
Yes.
The control signals are.
Yes. Yes.
So there are at one point of time the mobile is sending control signals
Yes.
and receiving from two different
Yes.
radars
Yes.
on the same channel.
Yes.
But physically the radio waves are same for data.
So that's what she was also asking, right? So the other channels are all located and so on for data, but the control part, right? You can change the frequency. That's okay. And so for the control, it's the same. See, at this point, although the channel is allocated, right? In that channel, the mobile has not switched to that channel. So this detail is missing in this time. The mobile has not actively started using that data part. And the control part it can use.
All the data part and control part, they're still on the same physical environment.
No. So data channel is different and it has different frequency, which is separate from. So this is control, and there is something which is data other than that. So these are all the details. We didn't talk about the physical layer and the map layer of these, right? So you are not aware of. So I didn't mention these details.
The actual signal that goes, the physical signal, the radio waves, they're also different for data and different for control.
Yes. Right? So there is a band that you use for data, which is separate from your control. And your control is always active.
The control must be shared between all.
And it also shares, right? So in fact, if you have a snooping device, I can snoop and find out which phone numbers are there and so on. Right? I can get a lot of information. That's what you see in the news, right? Typically, there is an antenna, and if you have the right hardware, you can actually start snooping on control messages meant for other people. You don't get their data, but right, the control information is there.
So, sir, at the certain time, the mobile device is connected with the control channel.
Yes. Yes.
Control channel for the data.
Right.
For data channel.
Yes. So this is for, so we are not going to go into details of GSM standard. There is another course for this, right, which talks more in detail about LG and 2G, 3G and even LTE, right? But this is because we talked about routing and how routing happens when you are mobile. I give you another example where within that region, how do you hand it off from one to another, and something similar will happen also on Wi-Fi. If you are in one Wi-Fi access point and you move from one room to another, right? This handoff, you can draw the same parallels and you can hand it off from one AP to another AP. So the last part of this is, and this last step, between the MSCs, what happens? So far we saw when you move from one cell to another cell, what happens? We saw when you move from one big area to another area, what happens? But this is when, so can you give me an example where you move from one location to another location without going between? So you are crossing the geography of multiple MSCs and you directly jump from one to which is very far. So if you board a flight and you switch off your phone and you switch it on at a very different place, right? You actually move from one to another without going through this. And but if you are, let's say, traveling in a railway on a road network, let's say, or otherwise road network, what in that case what typically happens is you don't jump like this. You go from one region with one MSC, then to another region with different MSC, and you keep moving across the cells with different MSCs. And if you are doing a long journey, so that hands-off are different. The way you do handoff there is different. So we're not going into details of that, but overall what happens is, see, this is how the call gets routed initially. You are here. Then when you go here, the handoff happens, like I mentioned, and so on. Now if you go from this cell to this cell, which has different MSCs, right? That's where your call gets routed like this through chaining. Right? This is a live call, ongoing call, and you're talking, and then when you move across from one MSC to another MSC, right, you use the chaining method. If you remember from the direct routing, right, I mentioned chaining, and that is how we do it there. Right? And if you keep on doing it, if you're lucky, right, you don't get dropped anywhere, right? Your call will get from one MSC to another MSC to another and so on. Right? And that's how you call. And that's why the chances of now, as you increase the chain, right, anywhere it can break, and whenever it breaks, your call gets dropped. Right, so your probability of drop call increases when you do like this. Right. Yeah, so as a protocol, it will keep on changing and it will get some optimal way of doing it. As you see, there are standards now evolving that since you can actually shorten this. If you find something like this is happening, right, through the chain, you can shorten the chain. But that's an optimization. That's not the protocol. So that's how you move from one MSC to another MSC. Now, if you now see all these hands-off that are happening, you send many messages on your control channel. You continuously scan your signal. So all that is overhead. So if you have noticed, if you are traveling in railway, your battery goes down very quickly. Otherwise, if it lasts for 1 day, but if you are traveling, let's say for 8 hours, 10 hours at stretch, going across, then your battery goes down very quickly. And the reason for this is because of all these control messages and hands-on. And you have to communicate more with the base station. And because of that, your battery dies very fast. And so if you want to avoid your battery to drain fast, and if you are traveling, the simplest way is to go offline sometimes. Right? That way, otherwise, even if you are not talking, your battery will die because of these control messages. Because it has to do this hands-off anyway, whether we are talking or not. So that's how, especially across MSCs, right? When you jump from one MSC to another MSC, it's big communication. So this, at the end of this, you will see a comparison between all of this GSM and mobile IP and what is similar between the routing and what is dissimilar between the routing. So let me stop this. At this point, we are finished with one topic, which is routing. But this routing is still easy as compared to what we'll see next. And this routing is when one node is moving, everything else is stable. Right? You are moving as a cursor, right? The mobile node is moving. Mobile end. And at the end point, you are moving. But if you see, everything else is stable. MSC is not moving, cell phone towers are not moving, the backbone network is not moving. So let me complicate the situation when the tower starts moving. And everybody is moving, nobody is stationary. Well, how would you do routing? Right? And that's where the challenge comes. And we'll see the protocols in this. These protocols are being used in military, right? But typically these protocols were designed by even agencies like NASA and ISRO. Any guess why? Why would NASA and ISRO be interested in something like this? Right. Inter-satellite or interplanetary. Right? If you want to create network between planets, right, the planets are moving, you can't stop planets. The vehicle, right, the spacecraft is moving, everybody is moving, there is nothing stationary there. Then how do you send messages from there to here? Right? So if you want to cross this galaxy, right, you should have a network where everybody can move and still you receive messages. And that's a very complicated problem. We'll not go into that level of complexity, but we'll still see a mobile networks with everything moving. And how do you do routing? So these are slides I borrowed from Intel, and Intel has published very nice takeoff slides on this topic. It's still a very active area of research, although the energy goes down and sometimes it's less, sometimes it's more. But can you think, how would you do if you are given a problem where everybody is moving? How would you do routing? So in other words, your parents are also moving, your home is also moving, your hostel is also moving. How would you do routing? Think of it, then I will give you how it is done. It will take a long time, to explain fully, but maybe I can give you some simple examples and then motivate. So for example, if I want to communicate with you, I don't know where you are, I don't know where your parents are right now, I don't know anything. How would I do it? I just know, let's say you're some ID, which is unique for you. You must have faced this situation, right? You're trying to trace a friend, right? Just nothing works out. Then how do you try to get in touch with that friend? Broadcast, right? Very simple thing is to do it, just talk to everyone. No matter who you met on the road, here, there, everywhere, just ask for that person, right? Maybe somebody would know. And then you tell that next person to also tell it to everybody else, right? And hopefully the word spreads out. And wherever you want, your final destination, that word reaches that destination. What should that destination do now? What is shortest path? Everybody has moved. Again broadcast, right? And then again that person starts broadcasting and broadcast, and hopefully it will come back to me finally, and then I get a message, right? Then how do you optimize it now? If let's say your communication is happening at the speed of light, so it's very fast, and people don't move at the speed of light, right? All the communication happens at the speed of light, the maximum fastest, right, speed. People don't move that fast. So how would you optimize this protocol? Otherwise, we can't optimize it. If you also start moving at the speed of light, right? Nothing I can do. In that case, maybe the protocol is, right, I just stand and let shout where, but hopefully that other person also, when he's moving fast, will come so close to me, I can just directly give that message. And that also is possibility. But let's say this people don't move so fast, so how would you optimize this protocol? Yes, very good, right? What happens is, if people are not moving so fast, you just tell that other person to remember from whom you got that message first time. And then everybody remembers it. The destination will get it, and destination will return that message immediately to that person. And that person has remembered from where I got it. So he will also return it back to that previous one. And hopefully if we haven't moved, there was no movement in all this communication, right? The message will immediately also reach back to you. In that case, I can now keep communicating till somebody moves. Right? So that is how that is where we start from there. And we start from there and we'll see the protocols. But that's how we can attack this problem. When everybody starts moving. Okay, and it's called mobile ad hoc networks. If you have heard this term, it's pronounced as MANE, mobile ad hoc networks. Everybody is mobile, everybody is ad hoc. You can't assume anything about anyone. And then how do you do networks? And that's a very big area. And again, this will give you some introduction. There is a course which is taught by Sanjay, which goes in detail about this. Right, so if you want more about this, you can again take that course. Right, so typically we know how routing is done on the packet switch network. What are the two protocols for routing? The standard ones. This question you will get again and again till you graduate. Two protocols, Bellman Fold and Dijkstra, or in other words, distance vector and link state. Right, so these are the two routing protocols. There is nothing else. Right? In the world, you can only have two routing protocols. Either it will be a distance vector or link state. Right? So whatever I will also tell you, will be some modification of distance vector and some modification of link state. There is no other way of doing routing. So in principle, I will come up and tell you what AODV and OLSR are, which are modified versions of the distance vector and link state. Okay. So before we start at the protocols, I will give you some idea of how to do routing at layer 2. Okay. And then I will tell you, I will just quickly summarize this protocol because I can imagine if you don't remember the names, I'm doubtful about whether you know the protocols. Right, so I will just quickly summarize it and then we start looking at it. So this is ad hoc mode, you know, and this is infrastructure. Ad hoc mode, there is no access point, everybody is like peer to peer, and anybody can talk to each other as long as they are within the range of each other. And in access point, all the communications are like this. If this one wants to talk to this one, it will go through the access point. Access point is your destination and your source for all communication. Don't talk. These nodes don't talk to each other directly. So, and of course, the one we are going to talk about more about is this one, right? Because here also access point is stationary. You assume your access point does not move. Right? So that's not a mobile ad hoc network. So, I don't know whether you have heard of this protocol, ARP. How many of you have heard about ARP? Good. Quite a few of you have heard about address resolution protocol. So, what it does is, it gives you a MAC address. If you know an IP address of any entity, use this protocol. It's like a database query in a way. And you get back a MAC address. If you want to talk to IP address 192 or something, you will use ARP. Gets its MAC address and create a frame using that thing as a destination MAC address, and you send that frame. And this is how the communication will work out. Okay, so that I think we all know, we agree upon. Now let me show you a scenario where I have an access point here, and my source is here, and my destination is here. My source IP address is 1.4 and my destination is 1.9. So this source cannot directly here and talk to destination. Okay? The source is on this side of access point, destination is on this side. How would the source send data to destination? This is a simple example. And you have to tell me in terms of ARP and everything. I show it here. But how would the communication happen? It's not telling you everything. It's just telling you the initial part. You have to stitch together the rest of protocol also and tell me if when this source sends a packet, IP packet to this destination, how would it send it? What should happen there? First thing, what? Yes. Right. But at this point, you don't even see at the MAC layer. What do you need to send data? MAC address, destination MAC address. Right. So first thing first, what does source do? It knows I want to talk to 1.9, right? But it cannot just use 1.9 and send it. So what should it do? It should. Right, so it should use the ARP protocol and try to find its MAC address. One thing is noticed that it's within the same local subnetwork. Right? Because it knows the subnetwork mask and the subnetwork address, it knows that this 1.9 is also somewhere close to me, within my subnetwork. But I don't know what is its MAC address. So it will use the ARP request. Right? It will send the ARP, it's broadcasted. Who will get the ARP request? Which one? All the nodes. But what will happen to that final request message? Who will reply that? Right. So in this case, let's say who will reply that. Right. So you're saying that this will come here, right, and get back a reply. But access point as it is will also have a reply for this one. See, access point is the one who has taken this other nodes into its coverage. So it knows its IP address and MAC address. Right? So it has this bit table built in already. So it will just look it up in that case. Right? It can send it, right? But there is no point also. It will have this information that one that lines MAC address is this one. Right? So it can immediately reply back. See, access point is the node which is monitoring all the nodes. So it knows IP address of all the nodes in its coverage and MAC address of all of that. If it doesn't know that, then how we communicate? We will get simple messages at the MAC layer. So it will send back a reply saying this node is there and this is its destination MAC address. So right now this source has got its MAC address, destination MAC address. What does it do with that?
It will send its own destination MAC address. It will send it to the destination MAC address in its own packet and send that to the AP.
No, it itself has the source. Right? So this will send a frame at the MAC layer, which will have source as its own and destination as whatever it receives. AP replies back with. Right? And it sends it. Who will receive it? AP will receive it because this is out of coverage as far as this guy is concerned. And all the communication in anywhere will happen through access point. Right? So AP receives it and AP will give it to the destination. So what is AP doing in terms of network protocols?
If you know all the IP and the MAC of its own network so that you can find out.
Yes, so AP should know all the IP addresses including its subnet and their destination MAC addresses, and it is doing the forwarding for all the data. Right? So if you have two laptops connected to the same AP, right, your AP will actually do the routing job at layer 2. It will take data, buffer it, and it will forward it to the destination. When the reply comes back, again it will take it and it will give back to the source. Right? So in this way, AP is acting like a router. Right? So data is going through the AP like this. Right? So it's acting like a router. So that's why this is a little different terminology. Typically, when we say routing, we refer to layer 3 network layer. But you see now at layer 2, AP is layer 2 device, but also it is doing routing. Okay. Okay, now that's the next slide. Right, so far good. If I want to talk within anybody in this classroom, I just use this AP and talk. Right, the packet never goes outside this room. All the packets stay within this room. Okay, now the question is this kind of a network. This is a node, there is another node, there is AP in between, and there is and so on. It's not directly connected by one AP. There are multiple APs, and within the APs, of course, you will have switches. The way APs are connected to each other is through the wired cable. And APs don't talk to each other directly. Right? So there you have these wires. So now our layer 2 routing will fail. Why does it fail? It's because there is no entry in the ARP table. Right? This AP does not know what is 10.0.2.8 or anything in other subnet. Right? It will say I don't know it. Okay, and that's where the AP fails, and that's where we need the real routing. How would you do that? Right. So, but we don't do it that way. If you start broadcasting every ARP request, right, it will be always the broadcast. Okay, so that's where we need a very nice way of routing. These are these two protocols, if you remember. Right? I mean, you can use broadcast, but then wherever you broadcast within the whole campus, right? And it just goes on. So that way we don't use a broadcast to that extent. Whenever we cross from one subnet to another subnet, so this is subnet 1 and this is 2. Right? You already know these protocols, how they work. So between two networks, if you go from one subnet to another subnet, use a distance vector or a link state routing. So if you see this subnet is 1.3, this is 1.1. So this is same subnet. But this subnet is different. This is 3 dot something, this is 3 dot something. So that's one another subnet. And there is a third subnet here, 6 dot something. So if you start putting subnets together, you cannot use ARP. Because you have to broadcast across how many subnets you broadcast. So you need a layer 3 routing. So if you talk to any Cisco person, right, he will say layer 2, layer 3. So layer 2 is the MAC layer, layer 3 is the IP layer, right? And if you are doing routing at this, it's layer 3 routing. So now, so I want to know what is the difference between these two. If you can think of this difference, I think then my job is little easy. From your memory, if you remember anything, what is a difference between, I don't want to know really what is a distance vector, how you execute all that. I don't want to know what is link state, and you do that. If you just know the difference between these two, just like we did between direct and indirect routing. Anybody has idea what is the difference? Okay. You all agree? Anybody says it is different? Anyone? So what she mentioned is in one protocol, right? You have information about all the nodes in the network, and in the other protocol, only the neighbors, right? Right. So these are the two protocols, right? Now the question is whether that connection is correct. And what happens in distance vector? You know everything in distance vector. How many of you say this? Anybody wants to differ? Right. So so you broadcast hello packets to everybody in the network. So what will happen in that case? Everybody will know where every other node is.
Everyone will reply with their own. They will establish a shortest.
No. Let her finish this one. So what she's saying is in link state you send a hello message everybody, and they will broadcast it again to everybody, right? And the message will go on. accept to itself, and
then people practice that source to cease. That's what they form.
right. But this hello message goes from A to B to their neighbor. What about C? Will C also get A's hello message via B? So in link state, how so? Not in link state. In one protocol, you get to know all the nodes in the network, right? You said, and there is a protocol in either of these two in which you get to know everybody in the network, right? So if C has to know about A, there has to be some communication coming from A to B and B to C. Otherwise, how do C know about it? Right? So the hello message has to go from here to here, and then from here to here, right? And that's how it goes. And that's what is link state. This in link state protocol, everybody knows about everybody, right? And that's why if you so the quick idea or way to look at this is to look at what these names are, and the names are not just given randomly, right? This only tells you about distance and a vector. That's it, and you send this vector across, and that gets modified. And it's a vector that gets modified. And in link state, every link has a state and you forward it to everyone. Right? So in this protocol, you will flood the network, in fact, with hello messages. And they just go to everybody else. Right? And that's how A will know that C is there, and C will know A is there, and of course B and so on. Right? So that's a protocol where you send it to everyone, and distance vector is a smart protocol. It doesn't send everything to everybody else. It just communicates with the next, and you exchange something. And what you exchange is that vector routing table. And then you see the details, but then this is the one where you don't know the entire network. You just know a vector. That for A, the vector is B is here. And if I want to reach C, what is the next hop? And what is the distance? Right? So that's the vector it knows, that's it. And it will keep exchanging these vectors. And once you know who is your neighbor and the vector, you can compute. So these are, by the way, complicated protocols. Right? And that's why it again gets confusing what is happening. But these are the routing protocols we use in this case, and the packet forwarding happens across the nodes. The criteria decide which is the least cost route is you first of all have to use the destination. You want to minimize the number of hops, or you want to minimize the distance, or you want to minimize delay. Sometimes the distance is less, but the time it takes is more, and it can happen. Right? But sometimes the distance is more, but the time is less. Right? So these two are different things. Minimize packet loss. Some nodes are very good in dropping your packets, some routers, but some routers don't drop your packets. So this is different from distance also and delay also. And then cost, finally. In reality, finally, it's all tied to finance. Right? Some routers will charge you more, and some routers charge you less. Right? So you want to minimize cost. Right? So you can minimize anything, but the protocol is the same. Right? So I would recommend you, before the next class, you revise what is a distance vector protocol and what is a link state. Because we can't start from scratch for these two protocols. And then I will tell you how these protocols gets modified. Now. Okay. So I don't want to then go into more details of these protocols. So what we looked at today is we looked at the cellular network and the routing within that cellular network. We saw handoff between one cell to another cell. Then we saw between two MSCs, how do you do a handoff? And then we saw across two different regions, right? How do you do handoffs? Right? And there are three different protocols for that. And then we looked at a network where the routers and everybody is mobile. Not only the mobile end node moves, the router moves, switches move, everybody in between moves, right? And we saw in that case we need the protocol. So before we look at the real protocol, I recommend that you summarize these two. Whether I might even put a quiz, right? Not graded quiz, but a quiz to understand whether you have learned these things. Right? See, if you don't remember this, it will be very hard to grasp the differences. Because I will directly jump into the protocols and then it gets complicated. So please remember to revise this. So let's start with it. Yeah. So the demos are over. We will very soon, by end of this week, we'll send you the marks for the proposal, one homework, and the demo. Everything.